welcome to Blueprint IoT. I hope you like this, a little bit of an unusual intro, but let's get right into the video about the Arduino UNO R4 Wi-Fi. It comes with some stickers and a nice welcome guide, and obviously it is very different. It has the LED matrix on top of it and the ESP32 soldered on top of it for the Wi-Fi connectivity. One thing I want to highlight about the Arduino UNO R4 Wi-Fi is its actual power, so connection, its interface, which is USB Type-C, which I think is quite a blessing for all of us. I think Arduino is here a little bit ahead of Raspberry Pi, which just recently launched the Raspberry Pi Pico W and 2W to Wi-Fi, and those are still on micro USB, which I think is not so nice from a user perspective. But anyway, that's it for the unboxing. In case you're more interested into the specs of the board and its performance, make sure to check out our video about it. But let's get right into the measurement. So let me introduce you to the setup here. We have a amp meter or multimeter, in this case used as an amp meter, on the table, which is hooked up to the USB-C cable that's supplying the Arduino UNO R4 Wi-Fi. So simply wall outlet here, and we have a little power device here, actually stolen from the Raspberry Pi. I cut the cable in the middle and hooked up the amp meter in between before the cable runs towards the Arduino UNO R4 Wi-Fi. And yes, by the way, super annoying, those cables with the ground around the main wire. I mean, I get it for shielding and everything, it's useful, and to keep the diameter of the cable minimal, but if you want to hook something in between, it's a proper nightmare to get it isolated, or but for this experiment it will be fine. So let's get started. All right, so the Arduino is plugged in, and you can see the code is already working because the first LED is on. So it's always 10 seconds interval, so it's 10 seconds the first LED. Now you see the second LED lit up, but if you kept an eye on the power consumption, the current is still like unchanged at 0.097 or 96 amps. Now we have one row, this equals 12 LEDs on at the same time, and still no change in current draw that we could measure. Now we have a random smiley, I think that's about 14, 16 something LEDs, still no change. Now we have all the LEDs on, and we can see 0.1 amp, so a little bit of increased power draw, 0.03 amps more. Now all the LEDs are off. This means the next step in the code is it will try to connect to Wi-Fi. So now, only now, the Wi-Fi got enabled, so we could see an increase in power draw now, so 0.16 or 17 amps, so actually 70% more than in idle just for the Wi-Fi. Naturally this difference will be big because it will now power on the ESP32 that's soldered to the board to connect to Wi-Fi. I wasn't too sure if it's like always on or always drawing power, but I think this difference in power draw is quite significant and basically shows us that the ESP is only engaged once you really engage the Wi-Fi. I made sure to not engage the Wi-Fi in this void setup. I put this part to engage the Wi-Fi, connect and everything in the void loop, so we have a clean measurement of functionality without Wi-Fi in the beginning. So now it will constantly try to connect to Wi-Fi, and I will quickly enable the hotspot on my phone to make sure that it can connect there. Alright, we are connected to the hotspot of my phone now. You can see basically no difference in power draw. It's like a bit more flimsy, a bit more up and down. And now it actually starts sending MQTT messages, one message per second. It connected to a broker that's not run locally, that's online. And I will quickly move out here with the video a little bit. I quickly set up my laptop here to show you guys the messages incoming. You can see every second a new message. So it's publishing like 20 messages. It goes from 0 to 10 and then starts again. So as soon as that's done, what's happened now, it will go into the same routine again. So what happens now is that the Wi-Fi is still connected and the LEDs are on additionally. And as we know, or as you can already confirm now, there is no significant difference. Just because the LEDs are on, it's still the power consumption mainly dictated by the Wi-Fi. And we can see the power consumption jumping around between 0.1 and 0.16 or 7. So that's obviously every time it tries to send something or tries to reconnect to the Wi-Fi or get some information from the Wi-Fi. And next up, it will again start sending, and we can see on the left hand side again on the laptop that it's again putting out the messages. But actually I couldn't see any difference in power draw depending on if it's sending an MQTT message or not. Needless to say that MQTT is a very efficient, power and resource efficient protocol, so it's quite obvious that it's not using anything significant from a processing point of view. But still, I think it's interesting that it's like sending or not sending is actually such a small difference that we can't even properly detect it. In case you're interested in having the same setup like this, but including a shunt and measuring with a scope to see the peaks a little bit better, let me know, and I will make sure to have the same setup as we had in the previous videos. But in the previous videos I not really saw any benefit of the scope because the power spikes and so on are so small and so short, so we can't really see it. So now it's again sending the MQTT messages, but once more, no significant difference. So obviously there's not a lot of processing going on at the moment. We have no sensors or stuff like this integrated. So looking at the overall power consumption, we are idling at 0.1 amp while not connected to the Wi-Fi. LEDs, no matter if it's 1, 2, 12 or all the LEDs, basically make no difference. But what makes a difference is turning on the Wi-Fi, because the ESP32 that's soldered onto the board gets powered, and we will end up at 0.17, so 70% more power consumption, 0.07 amps more. So we are idling at around 0.5 watt, which I think is really good. And even with the Wi-Fi engaged, and maybe let's assume we have a bunch of more processing going on, sensor readings, whatever, let's say it's 0.2 amps, you're really power efficient with just below 1 watt. So basically your power supply, I don't think you can buy a USB-C power supply with less than 5 watts, so 10 times more than what you need. If you're interested in building your own power supply integrated into your circuit, make sure to check out our video where we explain how you do this in the best way for Arduino or Raspberry Pi or whatever. So to have a reliable power supply and also providing 5 and 3.3 volt power levels, depending on the sensors you're using, you may need those two power levels, or even introducing 12 volts as the main voltage and then breaking it down to 5 and 3.3 for sensor and board, and having the 12 volts for your pumps or fans or whatever more power intensive applications. What you could do to save power, if you want to send the sensor data, wait whatever for a minute and then send all the sensor values from the last minute in one batch to power up the Wi-Fi only once you need it. We saw it at the beginning, idling at 0.1, and as soon as the Wi-Fi chip got engaged, we have a 70% increase in power demand. Obviously, that's all relative to what you have running in the background. If you connect now 10 more sensors, maybe using the PWM of the chip itself, this will also increase your power supply quite naturally. For a normal chip, let's assume you're only using the ESP32 as a standalone board. You would only power up a portion of the chip or subsystem of your board to use the Wi-Fi, while here in this setup you're powering up a complete separate microcontroller that's used to connect to the Wi-Fi. So you have a significant extra demand for the Wi-Fi because it's an extra chip, an extra board basically that you're powering up, while with another setup like a normal Raspberry Pi or Pico, Raspberry Pi Pico, or whatever other board you're using, or the ESP32 or 8266 itself, you would only power on an extra function of your board of your chip, but here you're powering on a separate chip. So just for reference, that's an ESP32 as a Node MCU or developer board, our breakout board. So you can see that this very same chip or very similar housing and packaging of the ESP32 chip with the Wi-Fi antenna on the Arduino as on the ESP board itself. But obviously the ESP board is much smaller, similar amount of GPIOs. You have different versions of those developer boards. I even have another one right here, just a different type of those developer boards. This one has, I think, an LED on board Those are both from Espressif themselves, the guys that are designing and manufacturing the ESP32, but obviously you have those breakout boards from several other suppliers as well. If you're interested in the power supply of the ESP32 or ESP8266 as such breakout boards or such developer boards or Node MCU, it's the one you would Google if you want to buy one, then check out our video about the power supply where we have the whole similar setup here, actually even including the shunt and the scope setup, where we're measuring the power supply or power demand, for those boards as well. Side-by-side comparison, also similar setup, like first doing nothing, then sending data and so on. So this may be a good comparison for you if you want to dimension the power supply or the battery size for your project. So that's it for this video. I hope you got a bit of a better understanding of the actual power demand of the Arduino R4 Wi-Fi. In case you have any other use cases you want to have tested or a different setup, as I mentioned with the shunt and the scope, you want to have a video like this, let me know down in the comments and I will make sure to change the setup a little bit. Currently I'm planning on having the next video about the Raspberry Pi Pico W to see the power consumption of this board, which was launched quite recently, and also a side-by-side comparison with a bunch of amp meters of different boards at the same time, so we can get a nice comparison. Before we close this video, I would like to ask you to drop in the comments what are you using the Arduino UNO R4 Wi-Fi for, and why you're not using the ESP32, because that's one of my main questions about this product. And also secondly, if you're working with it, basically where do you get your infos from? Because normally for setup like this, like a little code, whatever, I need like whatever 10-15 minutes, but in this case it took me 4 hours. Obviously I'm not used to work with the Arduino so much, I'm more used to ESP32, but still it shouldn't take so long. It was very difficult for me to have a setup. I tried obviously with ChatGPT, the latest version as of right now. It seemed like it wasn't understanding that I'm using this specific board, the Arduino R4 Wi-Fi. There was an Arduino UNO Wi-Fi version in the past, like quite some years ago, and I think it was still thinking I'm using this board. I wasn't aware yet that this board exists, even though this board is now on the market for, I don't know, maybe a year or so. So it really should know about it. But it was really strange, and also if you try to Google something, really little tutorials, and the whole setup with the ESP there soldered on the Arduino itself, like how do you actually talk to it and what you can use it for, it's all a bit confusing. And if you have a good place where you get infos and tutorials about the Arduino UNO R4 Wi-Fi, please let me know down in the comments, and also let me know what's the actual use case when you prefer using the Arduino compared to the ESP right away. So thanks for watching and thanks for commenting, and see you in the next video.